Our first speaker today is Rogemar Riffel of the Universidade Federal de Santa Maria in Brazil, and he'll be discussing AGN and feedback in the wrap up of that session. So Rogemar, if you're ready, you're sharing your screen, and please take it away. And Rogemar, if you haven't, you might leave your video on for you too, if that's possible. Is he unmuted?
Yeah,
I'm sorry,
yeah.
I'm not hearing anything.
Can you hear?
Okay.
Now?
Yes, I hear you and see you, and I see your slides now. Perfect.
Okay.
Thank you.
Well, I thank the organizers for the opportunity to share our recent results based on Gemini observations of nearby active galaxies. And the outline of this talk will be a short introduction. Then I will show some results on electron temperature distributions in three nearby luminous safer galaxies. I will present some results on ionized outflows from GMOS IFU observations of third local AGN. And finally, I will show some results based on NIFS observations of the molecular and ionized gas in the central region of nearby AGN and list my conclusions. So we know that the bulk of star formation and galaxy formation occurred in the first 3 giga-years of the universe. And we know that supermassive black holes form early from the observations, for example, of high redshift quasars, that supermassive black holes evolved together with their host galaxies from the black hole mass and central bulge mass correlation. And from simulations, we know that supermassive black hole form in the densest regions of the galaxies in their centers. Can you?
Rogemar, hold on one second. I think we might be having a technical issue with your slides advancing. We are still seeing your title slide. I apologize. There, now we're on slide number 4.
Yeah, you're just not showing, you're just showing the actual screen. I think you need to start the presentation.
No, I just started the presentation. Can you see my full screen?
No, we're seeing the window with, we saw it for a second.
Yeah, maybe I'm sharing the wrong window. Just a minute. Maybe this one. Can you see full screen right now?
No, we're still just seeing the, looking like you're editing your slides instead of the actual presentation.
And now?
No, I don't know if you want, see, we saw it for just a second. You did something and then we saw it it flashed up for just a second.
Yeah, I'm going to share a screen. Then maybe I have to, just a moment. No.
Maybe share a whole display instead of just an app.
No.
No, same thing. All right, so I don't know if you want to just you know, for time or whatever, just advance that mini window. Oh, there we go. There we go.
Yeah.
That's it. You got
Okay.
it. You're good.
So one of the main main goals of the extragalactic astronomy is to identify processes that transform galaxies from star forming to quiescent. And a way to quench star formation is by AGN feedback. And here I will focus mainly on AGN winds, which can be effective in suppressing star formation in some cases. AGN outflows are multiple phase phenomenon, and especially the most massive and molecular phase can produce shocks and affect star formation in the host galaxies. However, the multi-phase nature of AGN outflows is still not well understood, and questions like that, what are the geometries and the kinetic powers, are still open. AGN winds and shocks are hardly observed and hardly spatially resolved by observations of distant galaxies, but we can resolve AGN winds in nearby galaxies where supermassive black holes are accreting at lower rates. And an ideal tool to map AGN winds is by using integral field spectroscopy. And here we use optical and near-infrared integral field spectroscopy of the inner kiloparsec of nearby galaxies to map AGN winds. Most of the results, all of the results I will show here are published by the NIFS team in collaboration with several people here listed. All of them are listed here. And I will start by showing some results on the electron temperature distributions in the inner kiloparsec of 3 luminous Seyfert galaxies. The motivation behind these 2 papers published this year is that shocks from AGN outflows may affect the ionization structure and the electron distribution, especially in regions where the AGN ionizing photons are shielded by nuclear obscuration. However, there are no spatially resolved maps of the electron temperature in the narrow-line region of AGN, and we used high signal-to-noise ratio GMOS IFU observations to map the electron temperature in 3 luminous Seyferts. These 3 galaxies are Markarian 79, Markarian 348, and Markarian 607. They were selected from a previous work by Freitas et al. Just because they present the 034363 emission line and its flux distribution is spatially resolved by GMOS observations in each of these 3 galaxies. And so that we can use this line together with the strong 015007 emission line to measure the electron temperature. And here I show the maps for the 3 galaxies for Markarian 79, Markarian 348, and Markarian 607. In each panel, the black line shows the AGN ionization axis, obtained from the O3 flux distribution. And we observe that the highest temperature values are observed mainly away from the AGN ionization axis, outside AGN ionization cone, at least for Markarian 79 and Markarian 348. We also see a trend of higher values away from the AGN ionization axis, while for Markarian 607, the temperatures are smaller and consistent with photoionization models' predictions of AGN. In order to investigate the origin of these high temperature regions, we looked at the gas kinematics using the W80 parameter of the 035007 emission line. This parameter is just the width of the line that contains 80% of its total flux. And we see that the highest velocities here, the highest W80 values, are observed co-spatial with the highest temperatures. And when we plot W80 against the electron temperature, we see that there is a trend of increasing W80 with increasing electron temperature, providing kinematic signature that shocks are producing the high temperature values we observe. In addition, the O1 over H alpha line ratio correlates with the electron temperature. And we know that this line ratio is a shock tracer, so this provides additional support that the shocks play an important role in the observed temperature distribution ionization structure, at least in Markarian 79 and Markarian 348. So just summarizing these two papers, we use GMOS IFU to observe the central kiloparsec of 3 nearby galaxies. We use the O3 flux distribution to define the AGN ionization axis, and we found that the highest temperature, electron temperature values are outside the AGN ionization cone, and we attribute this to shock emission gas. A possible physical scenario for that is that these shocks are produced by AGN winds, which have a wider opening angle than the AGN ionization cone. Here, the blue arrows are showing the AGN, represent the AGN winds, while the green lines show the AGN ionization cone. So that inside the AGN ionization cone, photoionization dominates the production of the line emission, while outside the AGN ionization cone, we are able to detect shock emission gas. Moving to the second part of my talk, we used GMOS to observe 30 local AGN hosts. 13 of them were observed in the single slit mode, which provides both the blue part of the spectrum, including the blue emission lines and the red emission lines, and 17 objects were observed with the two slit mode, where only the red part of the spectrum is available, but the field of view is twice than the one for the single slit mode. For each galaxy in this paper led by Dutra et al., we present emission line flux distributions, velocity maps, centroid velocity map for each galaxy, and W80 maps for O3 and N2 emission lines for each galaxy, as well as line ratio maps and electron density maps measured from the sulfur 2 emission lines. We define regions, spatials, where outflows are observed as those with W80 larger than 600 kilometers per second, and have H-alpha equivalent weight larger than 6 angstroms. And when we compare the electron density distributions of the outflowing gas in orange here with the gas in the disk, we see that the electron density of the outflows are higher than the density of the gas in the disk. We compute the mass outflow rates by computing the masses using the H-alpha luminosity. We assume that the velocity of the outflow is W80 over 2, and the radius of the outflow is the distance of the maximum distance from the nucleus where a spaxial with outflows is detected. And here we plot the outflow rate against the AGN luminosity. We plot our results here together with some results from the literature. And we see that our sample populates the low luminosity end of this relation. And we see that the scatter in the lower luminosity is higher than for the higher luminosity AGN. Moving on to near infrared. In the near infrared, we can use the hydrogen recombination lines, Pachin beta in bracket gamma, as well as iron 2 emission lines to map the ionized gas kinematics. And we can use the molecular hydrogen lines in the K-band to trace the hot molecular gas. In a first study in the near infrared, we present J and K band NIFS data of 6 safer galaxies. For each galaxy, we present the emission line flux distributions, and we construct the emission line ratio, near infrared emission line ratio diagnostic diagram iron 2 over patient beta against A2 over bracket gamma. Here, red points are typical AGN values, while green points are higher than typical values observed in AGN. We see that the typical AGN values are observed mainly closer to the nucleus, while outside the nucleus we detect higher line ratios for both iron 2 over patient beta and A2 over bracket gamma. In order to investigate what's the origin of these high line ratios, we defined a function, an emission line ratio function, which is just a function of these two line ratios here, and plot it against the W80 for the iron 2 emission line. And we see that there is a trend of increasing of this function with the increasing of the W80, indicating that the high line ratio, the green sparkles here, are the emission of these sparkles is produced by shocks. This green region corresponds to about 29% of all sparkles in these 6 galaxies, while for the red sparkles, we see high velocities which are consistent with outflows, but emission lines are produced likely by the AGN radiation field. In a second work in the near infrared, we present K-band data of 36 AGN, which are all the AGN with NIFS data available from the SWIFT BAT catalog at redshift smaller than 0.1. 18 objects are type 1 and 18 are type 2, and they have very similar flux luminosities and redshifts. For each galaxy, we present flux maps and A2 over bracket gamma line ratio, and we construct an excitation map with the smallest line ratios consistent with star formation and the highest one by shocks. I will skip this one, as well this one. In the second work, we are looking at the gas kinematics in the same sample by presenting W80 maps, centroid velocity, and peak velocity. We define a kinematically disturbed region, likely due to outflows, just based on the values of W80 for the A2 over 330 kilometers per second, for bracket gamma over 400 kilometers per second, which are represented here by the red regions. We compute the mass outflow rates for the ionized gas and for the molecular gas. And for each galaxy here, there are 3 distinct symbols, which are just different assumptions to calculate the mass outflow rates. We detect outflows in 27 objects in ionized gas and 20 objects in molecular gas. We also were able to construct radial profiles of the mass outflow rate here for the ionized gas. And we see that the peak of the outflow is, the average value is 230 parsecs from the nucleus. And we compute also the kinetic powers of the outflows. Usually the outflows are not powerful enough to quench star formation. They are lower than 0.5% predicted by theoretical studies. And again, the scatter of the relation is higher here in the low luminosity end than the higher luminosity end. And here are my conclusions. We detect that shocks are important, play an important role in the electron temperature distribution. They are more important in regions away from the AGN ionization axis. We detect ionized outflows in 80% of the studied galaxies, with outflow rates from 10 to the -4 to about 100 solar mass per year. Hot molecular outflows are seen in 55% of the galaxies, and these outflows are not powerful enough to suppress star formation in the host galaxy and may just redistribute the gas within the galaxy. Thank you.
Thanks, Rogemar. Let's see. I don't see any questions in the chat. So let me ask a question of what, of the capabilities we have coming at Gemini in the future, what are you most looking forward to for this work? What would be most helpful to your future ambitions here?
Well, that's an interesting question, and I haven't thought about it. We still have some galaxies to be observed to complete our sample with NIFS, and likely we will not be able to conclude it before NIFS leaves the telescope. And likely we will use the Junior's IFU to complete our sample, but I don't know, we will need likely IFU data. So in the near future, we will still be using GMOS.
And I see one question in the chat here that I'll ask you, and if you can give a brief answer. Do you have GMOS and NIFS data from the same galaxies? If yes, does the iron 2 bracket gamma shock indicator follow the TE distribution?
Yes, we have NIFS data for some of these galaxies. And yes, we see that the iron Paschen beta line ratio is higher in the same region where we see the high electron temperature, for example, for Mercalli 79.
Great. Thank you again, Rogemar. Excellent talk. I appreciate it.